Okay, we're recording. So here's where we were last time. We were talking about this diagram, what I like to call this strategic diagram. It's just a way of organizing the objects and tools that we are using in the course. And I already spent some time talking about some of the ways that this is, patterns become visible, etc. Again, all of this derives from really natural, but unfortunately fairly sophisticated constructions that we can't actually show you in full detail. But the point is that this organizational structure still has very nice benefits simply because of the ultimate naturality of where it comes from. So anyway, one other thing I wanted to talk about is is how the diagram actually makes suggestions for you. It can help you solve problems. So for example, suppose you're trying to compute a line integral. Well, of course, it's entirely possible that the line integral can't be computed by our fancy methods, right? But you can see right here what your two options are. And for example, there is a possibility you might be able to use the fundamental theorem, and there is a possibility that you might be able to use Green's theorem. Okay, now let's talk about these one at a time. Can you use the fundamental theorem? The diagram tells you that whatever your curve is, you're going to have to compute the boundary points. No problem. That's just a matter of looking at your curve, however it happens to be phrased, and just identifying the boundary point. That's not an issue, particularly. More to the point, it also tells you that your vector field is going to need to be a gradient. Said differently, we're going to need to be able to identify the anti-gradient. I'm going to have to move from what I'm given, I'm going to have to move backwards through that gradient arrow, right? And so the diagram is telling you, if you want to be able to turn this into that, if you want to use this theorem, here's the challenge. The challenge is going to be to find the anti-gradient. Now, can you find the anti-gradient? The diagram suggests the way to arbitrate this, and that is that you compute Green's operator. Whatever your vector field was that you were given, compute Green's operator and see if you do or don't get 0. Okay. All right. So again, it's just a kind of a nice assistance that if you think in terms of the diagram, it kind of tells you what you need to be able to do. Here, likewise, let's think about Green's theorem. Can I use Green's theorem to compute a line integral? Well, whatever vector field I'm given, I'm going to need to compute Green's operator. No problem. A little bit of calculus, a couple of partial derivatives. You can always do that. That's not a potential problem. The problem is I'm going to need my curve, my boundary curve for that line integral. I need it to be a boundary of a region. Said differently, I'm going to need to be able to move backwards through this arrow. I'm going to need to be able to compute or identify at least the anti-boundary, right? And so again, it's telling you the questions to ask by way of just, the way the diagram is structured. So anyway, big fan. I hope you'll consider thinking about everything in terms of this diagram. For whatever it's worth, everything that I ever think about any of these theorems, I'm always in my mind thinking about, in the context of this diagram or, something analogous to it, because it is so very natural that way. Okay. All right, so moving along. Last thing we're going to do in this section is talk about how to compute antigradients. So I've been sweeping this under the rug for all of this entire section. Let's see where, here we go. So for example, when we first used the fundamental theorem of line integrals, in this example last time, I observed that the gradient of this function is the appropriate vector field. That's easily computed with a couple of partial derivatives. What I totally swept under the rug is where on earth did I get this function from in the first place? Right? It's one thing to take its partial derivatives. It's another thing to know, why did I think to take the partial derivatives of this function? It wasn't given. Right? Where did it come from? So that's what I want to talk about now. And again, it's sort of a computational trick here, how to find an antigradient. The observation to make is that if you want a vector field to be a gradient, well, that means that the coordinates of the vector field need to be corresponding partial derivatives. Namely, I need for these three things to be true. And then let me make the observation that, so for example, this statement about a partial derivative, I can kind of grammatically rephrase to be this statement about partial antiderivatives. Right? If the partial of f is p, then f is the antipartial of p. Right? That's the same statement, just kind of phrased backwards. Right? Okay, and then likewise for these others. Right? This is equivalent to that, vice versa. Okay, but when you write down integrals, don't forget you always have to say plus c. Why the plus c? Well, because the connection between these two statements is that when you take the corresponding derivative, here we're taking partial derivative with respect to x, constants go to 0. Right? The x partial derivative of a constant is 0, and so yeah, you can add in any constant you want. That's a single variable calculus observation. But here's the thing. Now that we're taking partial derivatives, far more than just constants will have their x partial equal to 0. In fact, if you think about it, any function that just doesn't have any x's in it will have partial derivative equal to 0. So, and it will therefore be a perfectly acceptable term, additional term in your anti-partial. Right? So that's the trick, is to remember that when you take these anti-partials, you do have to add in what we call partial constants. Okay. All right. So the question then of is our vector field a gradient boils down to, can I find a function that's equal to all three of these things? It needs to be equal to all three of these things. I just have to find it. Okay, and that is a little game that it turns out is an easy game to play, as in it's easy to win or it's easy to identify that you could not possibly win and you're going to lose. Either way, it's a matter of kind of straightforward looking. Okay, so here we go. Let's look at the process as applied to this vector field. Per the previous page, we take the x antipartial of the first coordinate. We take the y antipartial of the second coordinate. We take the z antipartial of the third coordinate. And these are easy antipartials to take. You get these functions right here. Oh, wait, I forgot my constants. Let's be careful about that. All of these partial constants over here you have to put in because they could be there. They don't make any difference in the partial derivatives. They're legal. So, the question is not, and it's easy to get wrong answers here. The question is not whether all three of these things are equal. That's not the question. The question is it possible for these things to all be equal? With the understanding that I can make these partial constants any functions I want, as long as they are only functions of the indicated variables. So let's play the game here. Let's see if we can win this game. So I see here there's an x squared y term. There's an x squared y term there. I feel like I'm going to need to have an x squared y. If all three of these things are going to be equal, I feel like there's going to need to be an x squared y term. But sad by the fact that there is no x squared y term here. But maybe there is. Maybe the x squared y term is what this partial constant function is. It's allowed to be any function of x and y. X squared y is a function of x and y. So how about that? Let's make this x squared y. We win. At least with regard to that term. Now let's go on xz. I feel like there needs to be an xz term in here, but there is no xz term there. Oh, wait a minute. Maybe there is. Maybe this is xz. Right? Now again, perfectly legal. It's a function of x and z as that is allowed to be. So again, everybody wins. Lastly, minus yz squared, minus yz squared. I feel like I'm going to need a minus yz squared here. There is no minus yz squared here. Oh yeah, well, yeah, you know what? Yes, there is. There it is. We can just let that be minus yz squared. And notice, as required, all three of these lines are equal to each other now. They're all equal to this. And so this is my anti-gradient. Everybody see how that game works? Okay. We won the game pretty easily here. It's just you got to think in terms of, there's only really one way the pieces can fit together and just make them fit together. Okay. Now, on the other hand, though, what if we lose? Sometimes we will lose this game. Sometimes we should lose this game. After all, there are some vector fields that are not gradients. You may recall this vector field right here. We talked about this one last time. Let me scroll back to it. This one here. We asked, is it a gradient? And we found out that no, it's not a gradient. Partly because of this computation about Green's operator. Algebraically tells us it's not a gradient. Or, if you like, we made an Escher-Stairs argument geometrically. It kind of just from the picture, there's no way that could be a gradient because those vectors can't all point uphill. There are no mountains that are shaped in such a way that those are all uphill. Right? So we know there is no anti-gradient to find. What's going to happen in the game if we try to find an anti-gradient that doesn't exist? Well, here we go. First coordinate, we take the x antipartial. Second coordinate, we take the y antipartial. And that gives us these terms. Don't forget about your partial constants. And thus begins the game. How am I going to make this equal to this? Keeping in mind, this thing here can only be a function of y. It cannot have any x's in it. And this can only be a function of x. No y's allowed. How are we going to make this work? I claim we won't. We lose. This is a losing game. We've already lost before the game started. So, thankfully, we didn't find any anti-gradient. How creepy would that be if we found an anti-gradient that doesn't exist? Everybody with me? So it's a nice little process, and that's how you find antigradients. And that, by the way, is how I found this antigradient right here. I played that game, and you can try this for yourself. Try that, play that game, and you will find that this is the winning move. Okay, all right. So that finishes chapter 6. We're going to move on now to chapter 7. Talk about parametrized surfaces. Just a broad overview, heads up. In chapter 7, what we're going to be doing is basically three-dimensional versions of what we did in chapter 6. All right, so in chapter 6, we talked about line integrals and double integrals, all in 2 dimensions. And how they relate to each other and the various operators, but all in 2 dimensions. We're going to move up now to 3 dimensions. And in 3 dimensions, you can talk about curves, you can talk about line integrals on curves, but more than that, you can also talk about surfaces and integrals done over surfaces. And the big accumulation theorems that we're going to develop are going to involve surface integrals. So in order to make sense out of surface integrals, we need to talk about how to parameterize a surface, and that's where we're going to start off. First, a broad description. The definition here of a parametric surface, it's very, very, very similar to the definition of a parametric curve. Remember, a parametric curve is just position as a function of one parameter. Parametric surface is just position in terms of 2 parameters. That's all it is. So here's an example. We have a formula here for position as function of 2 parameters, s and t. So this is a parametric surface. Now, what is this a parametric surface of? Well, let's kind of think it through. We seem to have here a vector x naught that is just sitting there. Doesn't move. Nothing happens to it. Right? What can I say about this here? Well, that is all possible multiples of this vector v1. And what can I say about this term here? Well, that is all possible multiples of this vector v2. And so one way you can think about this expression right here is that I'm going to start at this purple point, and from that purple point I'm going to move arbitrarily in this direction parallel to v1, and then arbitrarily from there in the direction of that vector v2. And so, well, if you think about it, I mean, if you're moving as far as you want in this direction, and then subsequently as far as you want in that direction, that's going to kind of sweep out this plane here. Hopefully this might look familiar. After all, this is a construction that we saw back in section 1.5. You may recall there was a homework exercise where the answer involved morally this construction. The details were a little bit different, but I hope that this looks familiar. Feel free to go back to section 1.5 and remind yourself of all that stuff. Okay. All right. Now, I'm going to show you now several tools for how to create parameterizations. Here, parameterization was given. Try to make sense out of what it was. We're going to do the opposite now. We're going to have some surface that we understand in some way. And we're going to try to figure out how to create a parameterization for it. Okay, first example. Oh, I'm sorry. I got ahead of myself again. Rewind real quick. Position in terms of two parameters. The thing about those two parameters, there's two of them. You can't think of them both as time, right? So this is one of the big differences between parametric surfaces and parametric curves. With parametric curves, we kind of lean on this very convenient crutch of thinking of the parameters being time, and then we can think of the parameterization as literally tracing out our curve. Position as a function of time, literally drawing out that curve. You just kind of have to abandon that here because we can't have two independent notions of time. It gets very science fiction and metaphysics, and it's weird. I don't think that's a good road to go down. Right? So that you have to let go of. Other than that, it's morally the same as parametric curves. Okay, so first tool for how to create parameterizations. A rip-off of something we saw for parametric curves, the graph parameterization. We had a graph parameterization for curves. And the idea was that if you're looking at a graph, that is, if you can solve for one of the variables as a function of the others, I emphasize you can't always, right? This is a hypothetical. If you can solve for one of the variables uniquely as a function of the others. Then the move is whatever the input variables are, let those be the parameters. That was the move in the curve case. Whatever the input variable singular was, let that be the input parameter singular. Here, there's two of them. That's the only difference. So let's look at this example here. Notice we indeed have a graph. The input variables, just as in our setup here, the input variables are x and y, so we're going to let x and y be s and t, just following the rule. And if you think about it, if x and y are s and t, that pretty much ties our hands. Z has to be s squared plus t squared. You don't have to decide to do that. You have to do that, right? So all you really decided, the only choice you had was to make this clever choice to let the input variables be the parameters, and everything just falls into place. So just remember that one trick: the input variables are the parameters, and it all works out. Okay, now in this case, Z was the variable that I had solved for. Alphabetically, that's sort of typical, but of course there's nothing magic about the alphabetical order. It could be that Y is the variable you solve for. Whatever. Doesn't matter. So, for example, let's look at this equation right here. I can't solve for Z. don't even try to solve for z. You can't, right? But it's easy to solve for y. So y is now a function of x and z. So x and z will be my parameters. And with x and z as my parameters, and y being a known function of x and z, plugging in those formulas for x and z kind of forces me to choose y to be that. And done. Parameterization, right? Check it out. I've got x, y, and z as functions of two parameters, s and t. Victory. Everybody happy? Cool. All right. You don't even have to restrict yourself to rectangular coordinates. Now things change a little bit if you use a different coordinate system. Here, notice I'm going to start by very first thing writing down my coordinate conversion formulas. But it remains all you have to do is to have solved for one of the variables in whatever coordinate system you're using. Here I've solved for rho, or maybe this was given to me with rho already solved for. And so I've solved for one of my spherical coordinates in terms of the other two. By the way, of course, there's no theta visible, but that's a good thing, not a bad thing. It's still a function of phi and theta. It's just a really easy function of phi and theta. That's all right. No problem. And with that being the case, I'm going to let phi and theta be my parameters. And notice that I kind of have to do that. I have to put rho. I have to plug in what rho actually is. And win. Right? We have now position. Let's see here. Yeah. Position as a function of two parameters, now phi and theta. Side note, why didn't I rename these as s and t? Well, because I don't have to. There's no confusion of variables here. I didn't want to have, x, y, and z as functions of x and y. That's a confusion of variables. Arguably, right? X and y are going to be inputs and outputs. That's not cool. So I renamed them s and t. Fine. That's just to avoid confusion of variables. Here, we're looking at x, y, and z as functions of already spherical coordinates. There is no confusion. You don't need to rename them. Unless you just want to, go ahead, feel free. It doesn't matter. Okay. All right. How are we doing? Is everybody on board? Everybody's happy. Okay. All right. Okay, this next example. This is a manufactured, weird example of a method whose applications are a little on the obscure side, so I don't want to spend a lot of time on this one. My main motivation on this is I wanted to show how something that we did with parametric curves could be used with parametric surfaces. In particular, the trick of using vector algebra to break down something complicated into simpler pieces. And when we were talking about curves, the example in question was with the bicycle wheel. Y'all remember the bicycle wheel with the reflector? And as the bicycle wheel rolls along, that reflector makes some weird curve. How do we parameterize that weird curve? And it was a hard curve, but it's a sum of much simpler vectors. They were just a matter of kind of writing them down, and then of course, adding simple things is still relatively simple, and so that was a very nice streamlining of the question. So you could do the same thing here. Now, it's a weird example I've come up with here, but I think it's as a broad stroke is a good idea. So here's my example. We have here a surface given as a graph. That's convenient. Because it's given as a graph, I can write down graph parameterization. That part's easy. We've done that already. What we have here, though, is that we're going to imagine that as the top of someone's head. We're going to imagine their hair, uniform hairs of length 1, and then imagine they grab onto that static electricity thing and their hair goes straight out, right? And like this, perpendicular to their head. And that makes a different surface. And the question is, how do we parameterize that purple surface? Okay, so that purple surface is a little bit harder to deal with. The vector observation to make here is that once you have, as we already do, a formula for points on the inner surface, all you have to do is add the vector representing the hair that's growing out of that point on the head. Right? And when you add that, that'll give you position on our outer surface that we want. So the purple points, kind of hard to write down initially, but the orange points are easy. The blue vectors are going to turn out to be pretty straightforward. And per the picture, orange plus blue gives me purple. Okay, so let's talk about these blue vectors. How do we deal with the blue vectors? I'm going to have to reconceive of this surface. This surface here, recall initially I thought of it as being a graph of that function. I want to reinterpret it, not as a graph. I want to reinterpret it as a level set. It's a level set of this function. Now recall we spent a bunch of time back in chapter 2 talking about the difference between graphs and level sets, and a graph of one function is a level set of a different function, and what's the relationships between those functions, blah, blah, blah. That stuff's unavoidably important. Keep in mind, if you apply the calculus of level sets to a function whose graph you're interested in, nothing makes sense, nothing works. Right? So you have to use the right kind of calculus applied to the right kinds of functions. And so all that graph and level set business is unavoidably critical. And it's also a little confusing, and so you got to take the time as needed to straighten all that out in your minds. And so if it's as a result of having been a while, if maybe you're a little rusty on all that stuff, please do give yourself the time to straighten all that out in your heads. So now reconceived, this green surface S reconceived of as a level set of this function, I can use the calculus of level sets as follows. Let's see here. This the gradient of G is always perpendicular to the level set of G, namely is always perpendicular to our green surface. And so there's a little bit of calculus of level sets, awfully convenient since we have the function for which this is a level set. And once I have that, then of course that what I'm actually looking for is a vector here of length 1 pointing in that same direction, and so all I have to do is normalize that dark blue vector, and that gives me the light blue vector that I wanted, and we are in business. And here's the final punchline. Then you may recall that we already wrote down that point there. So I've got the orange points parameterized, and I've got the blue vectors parameterized, and then orange plus blue gives me the purple surface that I wanted. So a little bit of weird manufactured. I don't know how often this is going to come up, but I do think it's a nice exercise in breaking a hard problem down into two much easier problems, and so I think it's worth showing you. Okay, moving along. This next method, really important, very commonly useful. Probably my second favorite surface parameterization tool. I got to go with graph parameterization for my favorite, right? But this is my second favorite. Basically the big idea is to create a coordinate system. And just create your own coordinate system, and then it turns a parameterizing question into a geometry question. So let me show you an example. I'm going to start with considering the torus here. Torus is kind of a donut-looking shape, right? It's just a surface, I emphasize. It's not a solid donut, it's just a surface. There. And how would we go about parameterizing this thing? Okay, well, we're going to create a coordinate system. Now, as we create a coordinate system, we're free to create any coordinate system we want. The goal here is to imagine that we are trying to describe locations on this surface, and we want to do so in the way that's the easiest possible. And let me start with a different example. Think about the surface of the Earth, right? You could imagine the surface of the Earth as kind of sitting in three-dimensional space, and one thing you could do, I suppose, to describe where you are on the surface of the Earth is give X, Y, and Z coordinates. That'd be super weird, right? Super weird. Super hard to deal with, to make sense out of. Nobody does that, right? How do we describe locations on the surface of the Earth? We do it with longitude and latitude. We say, look, you're going to be, a certain number of degrees above or below the equator. That's one angle. It's geometrically natural in the context. It's easy to visualize geometrically how that moves you along the surface. And then, rotating around is your longitude, right? So we, arbitrarily pick one longitude line and just measure, okay, well, how far do you rotate around from that? So it makes geometric sense in the context. It's natural and convenient. That's what we want to aim for here. Something along the lines of kind of a longitude and latitude kind of thing. It just makes sense on the sphere. So here I propose basically a kind of longitude and latitude of sorts as follows. You could imagine there being some sort of a kind of an equator on the kind of the outside part of the donut there. And, well, there's going to be an angle here kind of like latitude that says how much of an angle, starting at the equator, if you will, how much do you have to kind of rotate up sort of around the handle of the donut, if you will. How much do you have to rotate up to get to, that where you are? Fairly natural angle to talk about. Emphasis on the angle being measured from the center of the dough part of the donut, not from the origin. Right? This is an angle as measured from the center of the dough. Okay. And then next, this angle here, basically saying from wherever you might happen to be there, how far would you have to rotate around the whole of the donut to get to, the point where you actually are. Right? So anywhere you are on the surface of this donut, if you give me this green angle and this orange angle, I know where you are. It's very easy. It's very efficient. There's not extra angles that are extra distances or whatever that I don't need. It's very crisp and right to it. These two angles tell you where you are. What do you think? Yes?
Don't we also need to specify the radius?
Oh, yeah, but that's already specified up here. So the relevant radii are the sort of the what I'm going to call the big radius is A, and then the thickness of the that's radius is B. Okay. Totally.
But totally. If we made them not parameterized, we have to include those as variables as our parameterization.
I'm gonna say that the question that's before us is to parameterize a specific torus, okay, which means that the A and the B have to be given. Okay. Yeah, right. Okay. All right. So we have a coordinate system, and I claim this. Having made this choice for this coordinate system, it's just geometry from here. If I want to solve for X, Y, and Z as functions of S and T, it's all geometry. Let's do that geometry. Okay. So first, let's think about this as just to get things started. Let's talk about that point right there. I make the observation that is this vector, which is really easy to write down. That's just A, 0, 0. Points directly along the x-axis. We know that greater, sort of the larger radius is A, and so boom, that's just what that is. A little bit of trig will tell us that this vector, wrong color. This vector here, this blue vector here, is that right there. Now, there is some trig involved there. This is a good geometry exercise to make sure you're good with. This blue vector, keep in mind the length of this blue vector is b, right? From that being the radius of kind of the fat part of the donut. Given that angle, t, a little bit of trig on a little right triangle down there. Of course, this vector it's parallel to the xz plane, so the y coordinate is 0. To do the appropriate trig, you get this right here. Does that make sense to everybody? Good geometry exercise / trig exercise to persuade yourself of that. So now this red point that we're interested in, that's not our final point of interest, but this starting point, this red point, is just the sum of I'll do it like this. It's the sum of those. And so it's this right here. That's our red point. Okay, not what we're actually interested in. What we really wanted, of course, is this purple point. I want to know the point that's not just, the angle T up from the equator on the, if you will, prime meridian, but also, furthermore, around in the east direction, if you will, by this angle S. So, how am I going to take my understanding of this red point and generate this purple point from it? And the answer is a rotation. Right? So, I've got this red point here, and I want to understand this purple point. I can literally just rotate around around the z-axis. And if I rotate by that angle S, then that gets me what I want. And we know how to rotate vectors around axes. This is a linear algebra thing. You may recall one of the first things we talked about in the class, and I've hit it multiple times since then, right? But geometric linear transformations in the plane and in space is one of the biggest things that I need y'all to be good at from linear algebra. So we talked about it on the first day of class. It was in section 1.6, which I did first because, again, I think it just makes more sense as a prerequisite thing. And so check back to those pages of notes. Make sure you're good at producing, for example, a rotation matrix like this. The broad strokes to make sure you understand. First of all, rotations are linear transformations. Second, all linear transformations are matrices. Third, the columns of the matrix are the images of the standard basis vectors. Right? All of this is proved, or motivated at least, on in the notes in this course for section 1.6. And so to get these three columns here, all you have to do is just do this rotation to the three standard basis vectors. Little geometry problems ensue. And what you will find is that those three images of standard basis vectors are these three vectors here. Okay, so make sure you're good at that. Make sure you can do that this is a for example, right? If you're not sure, if you're a little uncomfortable with this would be a great thing to come into office hours and talk to me about. Very happy to talk about this one anytime. Okay, and all of that said, we are in business. We've got these red points. Let's see here. Let me do it like this. Direct geometry gave us these red points. The green rotation is this matrix. And you take the red point, you do the green rotation to it, and we're done. Position is what you get when you multiply all that out, which is this. I just multiply the matrix. Okay, so this is a parameterization of our donut. All right, now I want to remind you, what were we doing? Where did all this come from? What was the point to this example? Right? There's a bunch of geometry, a little bit of linear algebra in here, but the big idea is what I was saying at the very beginning. We created a coordinate system, and simply having created a coordinate system, the question turns into a geometry problem. Simply having written down that, okay, this is going to be my angle T, and this is going to be my angle S, and then it's just literally a geometry problem to figure out the X, Y, and Z in terms of those S and T. So, really nice trick. Again, it comes up a lot. There are a lot of surfaces where very naturally you can create a little coordinate system on them and then just do a little bit of geometry and you've got yourself a parameterization. All right. Okay, deforming a parameterization. Suppose I want to parameterize an ellipsoid. That's a hard problem. I can't solve for X, Y, or Z. It's not a graph. That's bad. Right? So we can't use graph parameterization. Well, here's what I'm going to do. I'm going to point out that we have an existing parameterization that's not that different from it. The unit sphere, easily parameterized, right? We talked about this earlier today. Rho equals 1. Immediately gives you, by the spherical graph parameterization, gives you this, aka that. That's this, this is kind of, if you will, a vector notation for that parameterization. This is sort of a coordinate equations for that parameterization. Okay, so what we have here in green is relatively easy. Spherical equations and all that. So, okay, here's the question then. Can I think of some way to deform the one that I have to turn it into the one that I want? And again, very often this kind of thing will arise. And specifically here, notice that what we started with was described by this equation. What I want is described by this blue equation down here. And what happens to turn green into blue? Wow, this is chapter 2 observation. I'm replacing X with X over A. I'm replacing Y with Y over B. I'm replacing Z with Z over C. I can tell you exactly how green turns into blue. All I have to do is stretch by a factor of A in the X direction, stretch by a factor of B in the Y direction, stretch by a factor of C in the Z direction. So the deforming is easy. The green parameterization is easy, the deforming is easy. So all I got to do is kind of fit those pieces together and I can get what would otherwise be a very difficult parameterization of this blue ellipsoid. Now, how are we going to do that? I'm just going to follow exactly what it says here. I need to stretch out in the X direction by a factor of A. I need to magnify in the X direction by a factor of A. I need all of my X coordinates A times as big. And how do I make the X coordinates A times as big? Well, I'm going to take my old X coordinates and I'm going to multiply them by A. That makes it A times as big. Simple as that. Right? And then likewise, I'm going to take my old Y coordinate that I need to be B times as big, and I'm going to multiply by B to make it B times as big, etc. Is everybody with me? All right. So deforming an existing parameterization is a really nice move. Now, here's a different way you can think about it. Another way that I can take, let's look at from the point of view of these equations. Another way that I can make all of the X coordinates A times as big. Another way I can stretch by a factor of A in the X direction is to replace X with X over A. Right? That was the chapter 2 approach on this. Totally fine. And sometimes students get confused. Wait a minute, should I multiply by A or should I divide by A? Well, it depends on what you're doing it to. If you're doing it to the formula for X, then you need to multiply the formula for X times A. If you're doing it by replacing the variable X itself, you replace the variable X with X divided by A. So we're doing different things, two different things. Right? And notice the answer is the same. These equations here are exactly the same as these equations here. All I've done is basically taken this A here, cross-multiplied to the other side, that gives me this over here. So it's all the same result, just how you choose to think about it. Okay. All right, so again, another tool for your toolbox. Sometimes you will find yourself needing to parameterize something. It's not a graph. It's not easily thought of in terms of sums of vectors. I don't see what the natural, easy, obvious coordinate system would be. Those other tools just don't work here. But it is very convenient to think of this as being a stretched out version of something I've already parameterized and then capitalize on that like we did here. Okay, another tool for your toolbox. Alrighty. So last comment before we go on to the next thing. The book does have several more examples. I just want to point out, I can't remember if I said this already, but I want to make sure I say this. The book's examples are all nice, but they're all what I would call kind of backwards. In sort of everyday life, in practice, if you need to parameterize something, usually that's the way the question comes. It comes in the form of, here's a surface, I want to create a parameterization. The book's examples are all backwards. The book's examples all start with a given parameterization. Given. And then ask, how would you figure out what the underlying surface is? Right? So it's just that that's not how questions tend to come at you. Most of the time, you have a surface and you need to create the parameterization. So when you're looking at the book's examples, I encourage you to think in terms of turning them around, skip down to the end of the example and see what the resulting surface is, and then try to reverse engineer it. Try to figure out how would you take the thing that they realized they had a parameterization for, how would you work backwards to create the parameterization yourself? Okay. All right. Okay, we'll do a couple more quick things before we call it a day. When you have a parameterization, keep in mind you've got position as a function of two parameters. I'm going to make the innocent observation that if you fix one of the parameters, well, guess what? Now you've got position as a function of one parameter, because one of them is no longer a parameter, it's now a constant. This is a silly observation, right? But if you've got position as a function of just the one parameter, that's literally the definition of a parametric curve, right? And depending on which one you fix, the other one is the remaining parameter. You can do it the other way. So there's two different parametric curves that you can make. These are what we call coordinate curves of that parametric surface. Okay, quick example. And we won't get to what we're going to do with this yet, but let's get this example done. Here's a parameterization. Let's consider what's happening at this point, or in the vicinity of that point, where we have certain values of phi and theta. Right? Notice this is our unit sphere, so that's the picture. And let's think about the coordinate curves. Let's talk first about the theta coordinate curve. The theta coordinate curve comes from fixing phi. We're going to nail down phi. Phi is now pi over 6. It's not allowed to change. It's no longer a parameter. It's just pi over 6. Period. Said differently, we are confined to that cone where phi is equal to pi over 6. And now let's think about what happens if I move theta. Right? If I go in the theta direction with the understanding that phi is stuck at pi over 6, well, then I just move along that intersection curve. And so this latitude line, you might call it, is a theta coordinate curve on the sphere. Is everybody with me? Okay. All right, real quick, let's think through the other one. What is a phi coordinate curve? Well, we're going to fix theta. Theta will be pi over 4. It's not allowed to change. We are confined now to this plane theta is now pi over 4. There is therefore only the one remaining parameter, and that is phi. And as I move phi with theta fixed, notice that just moves me down like that. That is the phi coordinate curve for that surface. All right. Everybody on board so far? Why we're doing this and what it's good for was going to reveal itself next time. So we'll go ahead and call it a week right there, and hope you all have a good weekend. Thanks for coming and braving the rain on a Friday afternoon. I appreciate you coming. See you on Monday. Have a great weekend.